So welcome to assignment number 4 or lab 4. So please ensure that your guest machine is running and also your host machine, you have logged into the host machine. Go to lab 4 and there you will find lab4.s, compile it, and now go to the log into the GDB. Set debug remote 0, set remote board 38400, right? 38400, target remote /dev/ttys0. So we are inside this, and now we can load lab4.out. Before we execute this lab4.out, let us go and see what this assignment is all about. This assignment teaches you till now what we have done in the lab 1, lab 2 and lab 3. We have not gone beyond privilege level 0. Now we will go to privilege levels more than 0. So what we are trying to do in this assignment is to understand how we can switch the privilege levels. And if I want to switch privilege level, basically we are doing it using tasks. So we will be creating 4 tasks: task 0, task 1, task 2 and task 3. Task 0 will execute at privilege 0, task 1 at privilege 1, task 2 at privilege 2 and task 3 at privilege 3. We will switch from PL0 to PL1 to PL2 to PL3, and at PL3 we will come and access a code which is PL1 through a call gate and then go back, and also prove certain things, like we will try and do at privilege 3 we will try and access a segment which is privilege 1, and then there will be a segmentation fault. So this is basically to understand the protection that is offered by the Intel x86, the x86 architecture, Intel or AMD. Right, and that is what we are going to achieve in this assignment. So to sum up here, we are actually in PL0 code section always. Till now we have seen that in all the remaining 3 labs that we have covered so far. Now what we will do is we do this PL0 to PL1 to PL2 to PL3. In PL3, from PL3 we will go and access PL0 code from PL and through a call gate. And again at PL3 we will try to access a PL0 or PL1 data, and then this will create a segmentation fault. It will give a general protection fault or a segmentation fault. We will see what sort of fault it is going to create, and then we will come back, and then after that we will return from PL3 to PL2 to PL1 to PL0. And here also we will see that since PL3 is causing a PL0 task, PL3 is trying to access a PL0 data, there is a interrupt that is happening, and the interrupt service routine will work at privilege 0. So we will also show that the stack corresponding to PL3 is being used, PL0 is being used. There is a stack switch that is happening, which I had explained, and that is very, very important from the point of protection. And then we will sum up this with all these things so that we have a full understanding of what is happening in this whole step. Right. So with this as the background, let us start looking at the code. So we will now see what is happening here very quickly. Now, as you see that we need to go and look at much more deeper understanding of the first few parts of uh, the code. So we are storing the, so let me just go here. We need to understand several parts. We are storing the GDT. Current GDT is stored at 0x. Code base is 8000 plus 3FFA DFFA. And this is 6 bytes. And now this is line number 6. Now we are storing the current IDT at 0xDFF2. It's again 6 bytes at line number 7. So, can we open it separately also? So we will open it separately. Yes. So we'll go up and down here. So I'm doing this assignment in full so that we have a good understanding. We move 0 to D200. 0x D200 is set to 0x def. This is line 11. 0x D208 is set to 1. This is line number 13. Then 0x DFF8 is set to 0, and this is line number 15. Why DFF8? Because code base is 8000, 8000 plus 3FF8 is DFF8. And also note that there will be a data segment to which this is adding. The current data segment which it is working at starts at 0. We have explained it earlier. It starts at 0. And we will also show that it is starting at 0 shortly. Right? Now we load. So let us go to line number 18. We load GDT with what is there in 0xD202, which is line number 18. So let us see the 6 bytes there. Now as you see, it is the GDT starts at D1000 and has a limit of FF. The GDT starts at D1000 and has a limit of FF. So the remaining 4 bits are 0 here, 0000 D1000, 00FF is the limit. So this shows that GDT starts at 0x D1000 with limit 0xFF. Okay. Now similarly, your IDT is loaded with 0xD20A. This is by line 20. So let us see what is there at that point. So it starts at D210, IDT starts at 0x D210 with limit 0x A0. Please see here. So D2 0 0 0 0, D210 is the base and 0 0 A0 is the limit. Now the most important thing that we need to know here is about the current IDT, right? Current LDT. So please see that LDT is loaded with 0x58. Okay, so where is 0x58? It should be x slash 2x 0x D058, because 58 is in the GDT, and as you know that the GDT starts at D1000 here, as you see here on your right hand side. So we load segment descriptor from 0x D058. And what is there at D058? Please note that this is giving me LDT that starts at 0x D100 and of size 00 FF. Okay, right, and this E2 basically tells you that this is a LDT descriptor. So this loads a LDT, loads a LDT starting at 0x D100 and of limit 0x FF. Okay. Now let us go to line 26, line 27. Your task register is loaded with that segment descriptor, basically 0x68. So look at descriptor in, again this is GDT at 0x D068. Why again D068? Because D000 is where your GDT starts. So let us go and look at the descriptor at S slash 2x D068. This basically gives us, if you look at 4089, this is a pointer to a task state segment. This is a TSS descriptor which is starting at B1000. Points to task state segment at 0x B1000. Please note that 70 is the limit. So it is given 70 is the limit, and you know the task state segment descriptor can be of utmost sense 104 bytes. So we are giving something more than a 104 size. This is basically the limit of that task state segment descriptor. Right. Now let us go and see that in detail here. So we'll just see here. So this is B1000. So let us go and see what was there in 0x68. 0x68. 06 B1000 limit is 70. It is a 32-bit TSS DCC. So this is the entire GDT that we have loaded here. Okay. Now, so the TSS now will be like this. It is starting at B1000, and your EIP will be stored at B1020, CS, DS, etc., etc., etc. So this is how your task state segment 0 will look like. Currently, we are loading everything and we are asserting a task state segment. Please note that these things are already loaded by the operating system. So currently, if you look at the task state segment, these things will be uninitialized because this current task is executing. The moment I am going to do a task switch from TSS 0 to say TSS 1, then all these values get filled up there. Okay, and then we go. Okay, now, so this is currently for the current task that is the first task that is executing, the values for these CS, SS and all these things will be initialized by the operating system. And when then there is a context switch, then that this TSS 0 will get filled with the relevant values. So first thing is we are just allocating a TSS segment for the PL0, but the initialization of all these registers etc. will not happen from this, because the operating system will do it. For the first 0th task it does. And then when we do a task switching, then the current values of TSS 0 would be at the time of task switching will be stored here. And then when these values, say suppose I go from TSS 0 to TSS 1, then these values will be automatically loaded. So the operating system will set up these values for TSS 1, 2 and 3. This should be TSS 3. This will set values for these, but for the first task, it is setting the value because it is allocating the TSS segment itself. So this is something that we need to understand here. Okay. So now I have allocated a task state segment at B1000 for the current task. And now I am moving all DS, SS, ES, FS, GS, everything as 0x10. So what is, so all your DS, SS, ES, FS and GS will have 0x10. This means what? This means, let us go to the 10th entry here. B1000 is base, FFFF is limit, and it is type data read write, and it is privilege 0. Privilege 0, this is means privilege is 0, base is 0x B000, and limit is FFFF. Okay, and this is for all, and this is done by whom? By lines 29 to 34. Now in line number 36, actually I jump to the next word. If you say D word, start minus code base. Start is here, code base is above here. Code base is starting here. So start minus code base essentially gives me how many bytes these instructions up to this, till including this. So from the beginning to this, the total bytes consumed by these instructions from the beginning of this program to this, that is what is start minus code base, right? So now I say jump 0x8. What is the 8? The scripta 8 starts at 8000. So 8000 plus the total number of bytes consumed by this to this, that will be nothing but this address. So when I do this jump 0x8 colon some start minus code base, I actually jumped into this instruction, but what I have achieved is my code segment now will be a different code segment. That is the one starting at 8000 with privilege 0 and limit BFFF. Okay. Now my CS essentially now becomes PL0 with base as 0x8000 and limit as 0x BFF. And this is done by line 36 of the code. Now I am initializing the flags to be 0 here. So I am making the location 0x. What is ds? ds is now b1000, b1000 plus 1ff0. 0x cff0. I am making it 0. And I am making ESP point to 0x1ff0. So when I say pop fd, now flags get initialized. Right? I'm initializing flags. So this is line 39 to 41. This is line 39, line 40. Pop fd pops the stack, so it pops the value 0 into the flag register. So this is line 41. So we reach this stage and now we start our code.